Hello students, topic of today's lecture is horn antenna. So first of all the question arises why the name horn is given. So as on the screen you can see the basic horn structure that is used by the vehicles. In ancient times the horn structure was made using the nose of the elephants. So with this structure the horn antenna is designed. So these on the right hand side of the screen, these horn are basically used by the vehicles like auto, trucks. And with the help of these structures the horn antenna has been designed. So now the question arises is that the first question, that is, what is horn antenna? So the horn antenna is an antenna that consists of a flaring metal shaped like a horn. Just now I have tell you the basics of the horn, where the idea of the horn antenna comes from. And as far as the antenna is concerned, so it consists of a flaring metal shaped like a horn. So there are certain characteristics about this horn antenna often have a directional radiation pattern with a high antenna gain which can range up to 25 dB. And it is in between 10 to 20 dB is a common, it's a typically in use. Now the question arises is that how the horn antenna can be achieve this much of directional radiation pattern. So the thing to tell you is that it is having a very high directionality, that is the directivity we can say. Now, how the directivity is achieved? Because its structure is designed in such a way that whatever input you are providing, almost all of the input power is getting transmitted in the free space. That means it is highly gain can be achievable with this horn antenna just because of its directivity. What is directivity? Directivity means how much of the power can be transmitted in particular direction by any antenna. As this horn antenna is very much useful in achieving the high directivity, that means the high gain that is in the range of up to 25 dB can be achievable with this horn antenna. Now the next characteristic, the bandwidth for a typical horn antenna can be on the order of 20:1. Means bandwidth, how do we find bandwidth? Bandwidth is simply find out with the formula, that is the higher frequency minus lower frequency, that is fH minus fL. So here with the help of horn antenna we can achieve a very high bandwidth. That means the fH value could be of 20 gigahertz, and the lower value, that is fL, is of 1 gigahertz. That means we can achieve a bandwidth of near about 20 gigahertz with this help of horn antenna. And the third characteristics, that is horn antennas have a very little loss, so that the directivity of horn antenna is roughly equal to its gain. Already we have discussed about the gain and directivity. Higher the gain, that is to be achievable just because of the higher directivity. On the right hand side of the screen you can see the directivity, you can see the horn antenna structure. Now we can see the constructional design of this horn antenna. Okay, so according to the Wikipedia, the first horn antenna constructed by an Indian radio researcher in the year 1897. Okay, but the ancient, we can say the modern design of the horn antenna was developed in the era of the World War II. That is, in World War II, the development stimulated horn research to design feed horn for radar antenna. Means basically the horn antenna was designed to support the radar. Okay, and in the year 1962, that is later on, a horn antenna has become widely used as a feed horn for microwave antennas such as satellite dishes and radio telescopes. Okay, feed horn means if suppose there is any transmission system, that time the antenna is located somewhat far distance from the transmitter. Okay, so we have to carry that transmitted power from the transmitter section to the antenna. Okay, means we have to provide a medium that should carry the power from the transmitter section to the antenna, and that is called as the feeding section. And that's why this horn antenna concept is basically used as a feed horn for the microwave antenna like satellite dishes and radio telescopes. Okay, in the figure you can easily see the radio telescope and whole model horn antenna. Now, how this horn antenna works? Okay. So, as we all of you are well known with the fact that how the general antenna works. Okay, the basic function of any antenna is just to transmit the radio wave into the free space. Okay, but directly radio wave isn't possible to generate. So whatever the data we need to transmit, the data is basically in the electrical form. So we need to convert that electrical signal into the radio wave spectrum signal. And how it is achieved? It is achieved with the help of some electronic circuitry that is used in the transmitter section. So what the transmitter section does? The transmitter section converts that data into the electrical section, and later on the electrical signal is getting converted into the radio spectrum signal. Okay, so that conversion of that electrical signal into the radio spectrum signal is done by this antenna. Okay, and the same principle is getting used by the horn antenna. So we can see the horn antenna converts the electrical power into the radio waves and vice versa. Means if we are using the horn antenna as a transmitter, that time the transmitter converts that electrical power into the radio waves, and if suppose we are using that horn antenna as a receiving antenna, that time whatever the power the antenna receive from the free space which is into the radio spectrum signal, that so that radio waves can be converted into the electrical signal. But when it happens, when that horn antenna is getting used as a receiver. Okay, so it is usually used with a radio transmitter or radio receiver. That means we can use this antenna either as a transmitter or as a receiver. The next point, it provides a gradual transition structure to match the impedance of a tube to the impedance of a free space, enabling the waves from the tube to radiate efficiently into the space. Okay, so as we all of you are very much familiar with the fact that every medium has this different impedance, we can say input impedance, right? So while transmission from one medium to the another medium, we first need to match the impedance in between that two medium. Okay, so here the horn antenna horn antenna structure can be used to match the impedance of the waveguide structure with the free space structure, as these both are having the different input impedance matching. And in the definition of the horn antenna, there the word has come, that is flaring structure. Okay, this flaring matter is usually, so this flaring metal is useful in this work to match the input impedance. Done. Now the range of frequencies used by this horn antenna. Generally, the horn antenna operates at a UHF and microwave frequencies above 300 megahertz. Okay, so we can, on the screen you can see the frequency spectrum. So in that frequency spectrum, there you can easily study, there you can easily see that in between the range of 300 megahertz to 3 gigahertz, that is the UHF range, that is being used by the horn antenna usually for the propagation. Now, waveguide. Why do we need to study this waveguide under horn antenna? So like I have told you, that any antenna can't be directly connected with the transmitter section. Okay, so before the connecting the any antenna with the transmitting section, here we will concern with the horn antenna. So we can say the horn antenna is getting connected with the transmitter section, that we need to fix any device, okay, in between that horn antenna and the transmitter section, and this structure is called as the waveguide, which we can say as a medium which is used to transmit the power from the transmitter section to the antenna section. Okay, so here waveguides are a rectangular or circular shaped tubes, and they are used for energy and information transfer in electromagnetic systems. Okay, as this antenna and waveguide, we can say they are just transmitting the electromagnetic signals. So these are the electromagnetic systems. So electromagnetic waves travels along with waveguides by means of a multiple reflections from the metallic walls. Generally, metallic waveguides have one conductor that is operates at a frequency above 1 gigahertz. Okay, so here in short, okay, how the signal is getting transmitted through the waveguide. Generally it works on the concept of the internal wave reflection, that the wave when falls onto the walls of the waveguide, it reflects back and getting transmitted, and further it is propagated. Okay, the same principle is getting used. The next, waveguide, it is continued. So the metallic waveguide is important component of many technologies with practical applications such as radar antenna, feeds, circuitry, waveguide slot, antenna arrays, horn antenna, microwave filter, and other various circuit components. So here on the screen you can see the horn antenna, which is connected along with the waveguide with the help of the flared structure. Okay, this flared structure is useful here in the impedance matching. Okay, here you can see the horn structure and the waveguide structure. On the right hand side of the screen you can see the horn antenna. Now the types of horn antenna. Basically this horn antenna is of two types, the rectangular feed horn and second one conical feed horn. A rectangular feed horn is again having subtypes like sectoral E plane, sectoral H plane, and pyramidal feed horn. Okay. On the right hand side of the screen you can see the structure of this sectoral E plane horn, sectoral H plane horn, pyramidal feed horn, and conical feed horn. Okay, is sectoral E plane horn. Why the name sectoral E plane horn is given? Because here the signal is, which we can say, or here we can see, in E-plane sectoral horn, the opening is flared in the direction of the E field. Okay, electromagnetic system signal consists of two field signal, that is E and H, that means electrical field and magnetic field. Okay, so here we can say the direction of the E field is perpendicular, right, to the H field, and the structure of the sectoral E plane is made in such a way that it is just parallel to that of the E field. That's why the name given is sectoral E plane horn. Okay. So here you can see sectoral E plane horn structure in that electrical field, and the sectoral E horn structure we can say the opening is flared, that is in the direction of the E field. Now the radiation pattern of the sectoral E plane horn. The E plane pattern is much narrower than the H plane because of the flaring and larger dimension of the horn in that direction. Okay, so here we can say on the screen you can see the direction pattern because of the E plane and H plane, but as here in the E plane section the dimension and the flaring structure is larger than the H plane. That's why the beam we are getting, that is the radiation pattern beam we are getting, is much narrower in the direction than that of the H plane, Okay, so here on the screen you can see in the blue color, that is the radiation pattern because in the E plane, and this radiation pattern that is in the black dotted line, which is the radiation pattern in the H plane, which is wider, and the radiation pattern due to E plane is narrower. Now H plane sectoral horn. In H plane sectoral horn, the opening is flared in the direction of the H field while keeping the other constant. That means here we can say the opening is flared, we can say that is in parallel in the direction of the H field and perpendicular to the direction of the E field, and that's why the name given is H plane sectoral horn. Now the radiation pattern, like in the E plane sectoral horn, where we are getting the narrower band in the E plane, that is in the E field. Okay, and here we are getting a narrower band in the H field than the E plane, right? So as on the screen you can see the blue color radiation structure is just because of the H plane, which is quite narrow than the radiation structure because of the E plane. Okay, and this narrower band structure in radiation pattern, that means it is just because of the higher directivity. That means the power is getting directed in the particular direction only. Now the pyramidal horn. Okay, just now we have studied the E plane sectoral horn and H plane sectoral horn. Okay, in pyramidal horn it is nothing but a combination of the E plane sectoral horn and the H plane sectoral horn. Okay, so here the most widely used horn in which is the one which is flared in both directions, and its radiation characteristics are essentially a combination of the E field and H field sectoral horn. तो उससे क्या होगा, अभी जो रेडिएशन पैटर्न बनेगा पिरामिडल हॉर्न की तरफ से, दैट विल बी द कॉम्बिनेशन ऑफ द ई प्लेन एंड द एच प्लेन रेडिएशन पैटर्न. Okay, so here on the screen you can see that, यहाँ पे जो फ्लेयर्ड ओपनिंग है दैट इज इन बोथ द डायरेक्शन ऑफ द ई फील्ड एंड एच फील्ड, राइट, बिकॉज इट्स अ स्क्वायर स्ट्रक्चर. तो नेक्स्ट वी विल स्टडी द रेडिएशन पैटर्न. अब यहाँ पे आप देख सकते हो कि एज आई टोल्ड यू इट्स अ कॉम्बिनेशन ऑफ द ई प्लेन एंड एच प्लेन. सो in the similar way we will get the radiation pattern that will be the combination of the E plane and H plane radiation pattern. Okay, so on the screen you can see that. Okay, both are having near about the same beam width. Okay, the blue color shows the beam due to the E plane and the black dotted structure shows the beam due to the H plane. Next, conical horn. So now here the conical fed horns are fed with a metallic circular waveguide in mono mode operation. Conical, as the structure is similar to the cone, that's why the name given is conical horn. Okay, and its mode of operation is in the mono mode. That means it can operate either in the E field or H field. Gain. So we will find out the gain. How the gain is getting derived. So here the basic formula that is to be used in the derivation of the gain is, it is simply a ratio of the output to the इनपुट. ओके, तो यहाँ पे हम लोग हायर गेन कब बोल सकते हैं, हम लोग किसी भी सर्किट का गेन हायर है या किसी भी सिस्टम का गेन हायर है, ये तभी बोल सकते हैं जब हम लोग उसको जितना इनपुट पावर दे रहे हैं तो मैक्सिमम ऑफ दैट इज गेटिंग at the output side. Means whatever input is giving, near about same thing we are getting at the output side. Okay, तो अगर हम लोग एंटेना की बात करते हैं तो यहाँ पे हम लोग हायर गेन कभी बोल सकते हैं, whatever the input power you are getting to the antenna, the same power is getting transmitted at the output side in the form of radio waves. Okay, that time we can say the gain is higher. So now as far as the pyramidal horn antenna is concerned, the gain is given as G is equal to 4 pi A upon lambda square into epsilon A. And for conical horn, the gain is given as G is equal to pi D upon lambda square into epsilon A, where A is the area of the aperture, D is the aperture diameter, lambda is the wavelength, and epsilon A is the dimensionless parameter, and it is usually lies in between the 0 and 1, and it is called as the aperture efficiency. Okay, तो ये एरिया ऑफ द एपर्चर क्या होता है, जब मैंने आपको फ्रीज ट्रांसमिशन पढ़ाया था दैट टाइम आई हैव एक्सप्लेन द कंसेप्ट ऑफ दिस एपर्चर. ओके, तो व्हेनेवर एनी पावर इज गेटिंग ट्रांसमिटेड इन द फ्री स्पेस at the receiving side, the receiving antenna isn't able to receive all this power. It will collect the only power which falls on the area of the antenna. ओके, तो उसको जो एरिया होता है जो वो पावर कलेक्ट कर पाता है, दैट एरिया इज कॉल्ड एज द इफेक्टिव एरिया ऑफ द एपर्चर. Now, why we use horn antenna? There are so many antennas But why we use this horn antenna? There are certain applications which leads to use only this antenna structure. Why? Because the antenna, that is the horn antenna, is having so many advantages which is hardly possible to provide by any other antenna. The first one, they can operate over a wide range of frequencies. As I have told you, the frequency range, that is in between the 1 gigahertz to 20 gigahertz. Okay, and such a band of frequency is hardly possible by any other antenna to provide. The second advantage, it is having a very wide bandwidth. That is means it can be, that is the horn antenna can be operate from 1 gigahertz to 20 gigahertz. That means the FL is of 1 gigahertz and FH is of 20 gigahertz. The difference in between that two will be the bandwidth. So the horn antenna can be allowed to operate over this much of band. Also, the next one, that is high directivity. This horn antenna is very much useful in the transmission of the wave, that is the radio wave signal, in particular direction. That means it is having a very high directivity. The next one, high gain. This higher directivity leads to attain a very high gain. If the signal is getting transmitted in only the particular direction, that time the spreading of the signal in any other direction is almost very much less. That is, we can say the loss is very much low. So whatever the power we are transmitting, this almost all the power is getting transmitted in the free space in only particular direction. Just because of that, the higher gain is achieved, which is hardly possible by other antenna like Yagi Uda antenna, where the power is getting transmitted in almost all around direction. But here the horn antenna, the case is something different, where we can achieve a higher directivity. Now the next one, support for wide applications. So we can say that every application has its band of frequency or range of frequency which is designed to operate in that particular application. Okay, and as the horn antenna is providing a wide range of frequencies, so many applications can be used this horn antenna. Now the applications of horn antenna, they are used as a feeders for larger antenna structures such as parabolic antenna, as the directive antenna for such a devices as radar guns, automatic door openers, microwave radio meters. It can be also as a common element of a phase array, satellite and microwave communication, used in the calibration. Other high gain antenna used for making electromagnetic interference measurement. So these are the applications of the horn antenna. Next one, references. For making this presentation, I have referred the Balinese and a Wikipedia. Thank you.